In this video, we're going to talk about exponential functions. First, we need to talk about the laws of exponents. So these are things that we've seen in practice before, but they come in handy with exponential and logarithmic functions. So keeping in mind that anything that you do to exponents, they have to have the same base. So for example, if I have base a to s and base a to the t, if I multiply them together, I just add the exponents. And a power to a power multiplies the exponents, and then distributing an exponent goes to both bases. 1 to any number is 1, and then a negative exponent throws that base and the exponent into the denominator. And then anything to the 0 power is 1. Something else I want to touch upon is the difference between exponential and power functions, because they're easily confused. So an exponential function is some a to the x, where a is a rational constant that's not equal to 0, and a power function is x to a rational number. So the basic difference here is that this red graph here, 2 to the x, is an exponential function, where x to the power of 2 is just a power function. Next, let's talk about linear versus exponential growth. So an exponential function is defined as something like f of x equals c times a to the x, where c is something that we call the initial value, that's usually our y-intercept, and then a is my growth factor, so that's the thing that causes the exponential growth. Now, sometimes it's hard to identify whether a function is going to be linear or exponential or neither just by the given graph. So I'm going to show you how to analyze 3 different types and determine whether they're linear or exponential, or neither. So here's that first function table. So my inputs are under x here, and my outputs are for y here. And if I was to find the change in y over x, which is also called the average rate of change, or you may know it as slope, of each point between x and y, so between this x and y and this x and y, the change is -3. Between these 2 points, it's the same, and it's the same for every pair of points going down the line. So that's going to mean that every time I move from one point to the next, it's going to drop -3 over 1. So that's a linear function. Something else to note is this ratio of consecutive outputs. And I can determine those by taking the y values. So here it's 2 over 5. I take the second y and I put it over the first y. As long as I am going up by 1 on the x, so -1 to 0 is by 1, 0 to 1 is by 1, etc. So I just take this y, 2, and put it over 5. So that means that the y is changing by a factor of 2/5, and then -1/2, and 4, and 7/4. So because that's not the same, I know that that's not exponential, but because these are the same, I know that that's linear. So I'm going to write the function for this as f of x equals -3x plus 2. That -3 comes from the average rate of change, and that plus 2 is my y-intercept at 0, 2. And here I have my second table with my inputs and my outputs. So each of these represents a point on the graph. And I first find my average rate of change, so change in y over change in x, and I notice that they're different rates of change, unlike the last table of values I had. But it seems like there's a pattern here. -16, -8, -4, and -2, that might create a pattern. But then what I look to is my ratio of consecutive outputs. So that means that 16 over 32 is going to be 1/2, and 8 over 16 is 1/2, 4 over 8, and 2 over 4 are both 1/2 as well. That points to an exponential function. So if I was to write the function for this table, I would start with my f of x equals c, which is my initial value, and that's always at the y-intercept, so that's 0, 16, so 16 is c, times a to the x, and a is going to be my consistent ratio of consecutive outputs. So if it's the same here, a is going to be this value. So it's going to be f of x equals 16 times 1/2 to the x. And here's my third table. So here are my inputs and my outputs. And I find my average rate of change to be 2, 3, 4, and 5. So that's not the same. I know that that's not linear. So then I go to my ratio of consecutive outputs. So I would do 4 over 2, that's going to give me 2, 7 over 4, 7 fourths, 11 over 7, 11 sevenths, and 16 over 11. These aren't the same and these aren't the same. So this function is neither linear nor exponential. And for right now, we're not going to worry about writing a function for this. Now let's talk about the graphs of exponential functions. So let's first talk about the basic or parent exponential graph. So that's something like f of x equals a to the x. So there's two scenarios. First one we're going to look at is when a is greater than 1. The thing to know about this type of graph is that the domain is going to be all real numbers, and the range is going to be 0 to infinity, not including that 0, because I have a horizontal asymptote at y equals 0. There's not going to be any x-intercepts, but the y-intercept is 1. So that could change based on our c or initial value, but for this instance, we're just going to take into account that c is 1. So this is an increasing function, like we said, and it is 1 to 1, meaning it passes the horizontal line test. And what's really important are 3 different points on the graph. So 0, 1, because anything to the 0 power is an output of 1. And then if I put in -1, it's going to be 1 over that a value. And if I put in 1, I get out the a value. So depending on what your a is, these 3 points are classic, and you should commit those to memory. And also, the graph of f is smooth and continuous. There's no breaks, there's no corners, no gaps. It's good to go. And then the other parent function scenario is when I have an a value here that's between 0 and 1. So that's some kind of fraction. And the domain is still going to be all real numbers for this, and the range is going to start at 0, not include it, and go to infinity, just like the last one. The y-intercept, same thing, is going to be 1. And then it's actually going to decrease, because if my exponential growth is by something like 1/2, of course, each point is going to get smaller by a factor of 1/2, hence decreasing. It's still going to be 1 to 1. It's going to pass that horizontal line test. And then the points are going to be the same, -1, 1 over a, 0, 1, and 1, a. Like I said, commit those to memory. And of course, this thing is going to be smooth and continuous, no corners, no gaps. So I can take a look at this example here for when a is greater than 1, so like y equals 2 to the x. And then when it's a fraction, I can have y is equal to 1/2 to the x. Notice that 2 to the x is increasing, 1/2 to the x is decreasing, and that -1, 1 over a here, 0, 1, 0, 1, 1, a, 1, a, those still exist, horizontal asymptotes at y equals 0, 1 to 1, smooth and continuous, all that good stuff. So really, you need to pay attention to what the a is telling you. If it's greater than 1, it's going to curve up. If it's between 0 and 1, it's going to curve down like that. And something that comes back into play when we talk about graphing exponential functions is, of course, transformations of functions. So let's take this example here, f of x equals 2 to the -x minus 3. So if I was using transformations, I would take my original function, 2 to the x, I would reflect it over the y-axis for that -x, and then I would drop it down 3 on the y-axis. So that means that my domain stays the same. That's going to be all real numbers. The range is going to start at -3 and go to infinity, and the horizontal asymptote is no longer at y equals 0. It's going to drop down 3. So the horizontal asymptote is going to be at y equals -3. And last thing I want to talk about is solving exponential equations. So that's a situation where I have to have the same base, so something like a, and that would mean that if it's a to the u equals a to the v, u is equal to v. So I'm going to use that to help me solve 3 different equations for x. The first being this one, 3 to the x plus 1 equals 81. First thing I have to do is find the same base for these two numbers, 3 and 81. Now I know that 81 is equal to 3 to the 4th. So I have the same base. That means that I can take this x plus 1 and set it equal to 4 and solve for x equals 3. And I always want to check just to make sure that my solution actually works in the original. And for this situation, it does. Here's my second example. 4 to the 2x minus 1 is equal to 8 to the x plus 3. First thing I realize is that I can't transform 8 into the base of 4 and vice versa. So I have to find a new base that's not 4 or 8. I noticed that 2 squared equals 4 and 2 cubed equals 8. So I have my 2 times 2x minus 1 and my 3 times x plus 3. I set that equal to each other and I solve for x equals 11. And I check and I get a ridiculously large number for both, but they're equal to each other. Now I saved the best example for last. Let's solve this equation here for x, and just in case you don't know, e is a mathematical constant that's equal to about 2.72. We use it in natural logs, so we treat it as just a regular number. So we're going to solve for x. But first I have to simplify it, so I have e to the something equal to e to the something else. So the left side of the equation is fine. It's e to the negative x squared. So this ends up being x times 2, so that's e to the 2x, and 1 over e to the third is saying e to the negative 3. So I have the same base. When I multiply, I add the exponents together, so that's e to the 2x minus 3. So that means I have the same base here, and I'm going to bring down the exponents and solve for x. It's a quadratic, I can factor it, and x is going to be equal to negative 3 and positive 1. Last thing I have to do is check to make sure that both of these work, and negative 3 is going to produce e to the negative 9 on both sides, so that works, and x equals 1 is going to produce e to the negative 1 on both sides, so that works. And that's going to do it for this video. Thanks for watching.